Good morning, and welcome to our talk, Moving People with Closure.
Yeah, hi, I'm Karthik Gupta. I work at Gojek as a product engineer.
And I'm Abhinav. I work at Nilenso Software, which is a software consultancy, and I'm currently consulting for Gojek. So this is an experience report on how we rewrote a very integral service at Gojek into Clojure. So this is a sort of a quick talk because we have a lot of ground to cover. So we'll take the questions in the end, and you can, of course, see us later for more details.
So many of you will not be familiar what Gojek is. Gojek is an Indonesian startup for transportation, logistics, and payments. It was founded in 2010, and it is the only unicorn in Indonesia. It operates over 25 cities with over 300,000 drivers, including both bike drivers and car drivers. And we have more than 25 products. And we process over 1,000 orders per sec.
The interesting thing here is that we use the same fleet for all of these 25 products. You can see some of them on the screen. There is ride, car, food, courier, and groceries and such.
Yeah, this is how our Gojek customer app looks like. So how all it got started. So in 2015, Gojek used to take orders through phones. So customers used to call customer care to book an Gojek. And in January 2015, our Play Store app launched. So at that time, we had around 800 drivers. So by August 2015, our business grew 5x, and we had around 30,000 drivers. And then we started to pull allocation-related code from Java monolithic into Golang service.
So as you can see on the slide, at the beginning we wrote a single service which was in Java, which did everything. But as we started new verticals like courier and food and search, we decided to move to a microservice-based architecture, and we sort of split out these things, and we also pulled out the driver allocation related code into a Go service. This was August 2015, and we did this because, the promised performance and concurrency support of Golang. So this code, yeah, go on.
Now, as business grew, we hired more drivers, that 200,000 drivers in Feb 2016. Now, business wanted to experiment with bookings, with new allocation strategies. And so writing domain logic code in Go was tough or became difficult. And so in August 2016, we decided to rewrite our allocation service app into a Clojure service. And by October 2016, we finished the rewrote as in feature parity with our old service. And we spent a month on testing and releasing it. And by November 2016, it was in prod. Yeah.
So the rewrite itself, this talk is essentially the story of the rewrite. So before we jump into the rewrite, this is what allocation looks like, driver allocation, right? So many of you may not be familiar with this domain. So this is a very simplified architecture. You have customers on one side asking for, different things, food, courier, whatever. And these orders go to the order management systems, right? The order management systems take care of the particulars of the booking, whether it's food, courier, bike ride, or a car ride. But they call the allocation service for actually finding a driver for the particular booking, right? So the allocation service contacts the possible drivers, whoever is near that area or depending on some criteria. And if the driver accepts, then the flow goes in the reverse order. The callbacks happen. The driver app will call back the allocation service saying, hey, I have accepted this order. The allocation service will call back the particular OMS, and the OMS will finally call back the consumer app saying, hey, you've got a driver now, right? So this is basically how the allocation looks like in the old as well as the new service. The essential architecture has not changed. So why did we decide to do this rewrite at all? So the Golang service actually ran fine for a whole year, right? We did not face any major bugs or issues with it. It was quite performant. But as the code base grew, we found that it became very difficult to add new features. Go, if you're familiar with it, it prefers a mutation-heavy and imperative code base, essentially. And this app was not a simple app which basically saves just data in database and shows an API over it. This was a lot of domain logic. There were a lot of rules about how to choose drivers and such. So the domain code was very hard to reason about. I admit that there were a lot of issues on our side also. We actually did not know Golang that well at that point. But soon we realized that adding new features and being able to tweak the strategies is more important than high performance, which Go promised. So we decided to rewrite this into Clojure about a year ago. So we found that the features the Clojure provides, immutability, laziness, and dynamic typing, leads to a much simpler domain-specific code, right? So I will show you a sample slide. I'll show you a sample code. This is how it looked like when you had to choose a driver for a particular booking. You can see this Go code. It's huge. It has a lot of if, continue, break, returns, nested, control flow, and strange, domain logic mixed in, right? But after we did the rewrite, this is essentially how the Clojure code looks. Much simpler, right? You just add, this code is way more extensible than the before because you just add new filters in between however you want. Filters are lazy and they're easily composable. Whereas the Go code required you to it was very mutation heavy and you changed local variables and put things in arrays and stuff. So it was difficult to maintain. This Clojure is in fact so easy that now when the business folks ask us, how does allocation work? We just show them this snippet and they understand, right? So it's, we found that Golang was essentially hard to use for writing complicated domain logic. If you want to focus on the specifics of this code, we get a bunch of drivers from some other service, and then basically we filter out drivers depending on some different criteria by balance, by rating, and etc. And then finally, we get another bunch of drivers to which we send the booking. So this rewrite was done in 2 months with a pair of people working on it. We achieved feature parity, and after that, we decided to test the rewrite very rigorously because this was at the very core of the Gojek business. All the order management services talk to this service. So how did we test the rewrite? We spent 2 weeks in testing. The testing methodology was a bit unusual. Instead of using, we of course did a lot of unit testing and such, but instead of using a load testing or such, we decided to test this on live traffic. So this is how our testing infrastructure looked like. So you had the apps, the driver apps, and the consumer apps calling the same order management systems. The order management system will send the live traffic to the Go allocation system. But we had a tool, it's called Go Replay. It's actually written in Go. So it taps into the network and basically sends your duplicate traffic to another server, right? So we send the duplicate traffic to the Clojure allocation service. And so we needed to have the Clojure allocation service no external effects. It needed to be isolated because it was in testing. It was not a production-ready system yet. So we used feature toggles to toggle off some of the downstream services to shut down the real-world effects. And for other services which we needed to have running for this service to work, we created mock services, which implemented the same API as the actual service, but did not have any external effects. So, and some services like cache and such, we had to share with the the older allocation service, so that the data is correct. So we ran in this mode for about 2 weeks. We found bugs, we fixed them, we captured all the data, the transactional data in the database, and the external world effects elsewhere in the mock service logs, and then we matched them. We matched the Golang allocation data and the Clojure allocation data, and we matched it till we found a perfect match. So this went on for 2 weeks with full traffic. After that, we decided to release the rewrite slowly, incrementally. First of all, we use a AOT compiled UberJar as a single deliverable, right? I'm not sure how many of you use UberJars as deliverables in production, but we decided to go with this. We compile it because we realized that it saves us almost 10 to 15 seconds of startup time. The compilation is a bit slower, but the startup is faster. We added lots of monitoring around the service. We added monitorings for application metrics. We added monitorings for domain-specific business metrics. We added error monitoring. And then we slowly rolled it out over 2 weeks. So this is how the rollout looked like. So we changed a bit of code in the OMSs to one particular OMS to send 1% of live traffic to this new service and rest of the traffic to the old service. And these services shared the external downstream dependencies completely. So we ran in this mode for a few days, then we increased the traffic, then we really slowly switched over one OMS over completely, and then over a week, we switched over all the order management systems. And at the end of the week, we had whole of the Gojek running on this Clojure service, right? So this was actually a fantastic way this is actually a good way to get Clojure into your company if you want. So you match, run it in like a side-by-side match data, and then do a gradual rollout, right? So we did not face any major bugs, and the release was very smooth.
So we learned some lessons, and I'll share some with you. Okay. So we use generative testing. So as this is the core of Gojek's business, we wanted to test it very rigorously. So as you can see, we have testing at all level, unit, functional, and integration. And we have around 100,000 assertions in just 150 tests. We used TestTech library, and we wrote our own generators. I'll show you one booking generator. So this is our booking generator with some fields and native generators. Like we wrote this all generators like pause integer, latitude, longitude, JSON, URL. So this is one sample test which checks for this is an API test which checks for the booking into the DB. Like it creates a booking into the DB and checks if it is same or not.
So if you see that number over there which says num tests 100, that basically means that run this test 100 times, right?
So while developing, in initial phase of development, we caught a lot of bugs because of like generative testing, and so we fixed those bugs, and this led us to do a faster release cycles. Now, as generator produces random data, now there should be something to validate that data. So we used Prismatic schema to validate our data at all API levels and config levels. So this is how a booking schema looks like.
Pretty similar to the
corresponding
generator. In fact, schema provides you a way to generate data from schemas itself, but we ended up not using it because it was too slow. And if you're wondering why we used schema instead of spec, at that time, spec did not have generation capabilities, and schema provides us coercions, which spec doesn't, or as far as I know.
So we have Swagger integrated with our app, and it uses the same schema as this Prism, the schema. So it is easy for others team to integrate with us. Now, if we are talking about external integrations, now what if external dependencies gives the errors out or gives a failure? So to defend our service, we use the circuit breaker. So we wrap an external call into a circuit breaker, which makes a call and monitors for failure. When a failure reaches some certain threshold, it trips the circuit, and after some time, it checks if the downstream service is up or not.
So the diagram explains how the circuit breaker works. We wrap all our external calls, because this is a central service which calls a lot of downstream dependencies, into the circuit breakers. If something goes down, it does not affect our service. The circuit breaker also supports fallbacks fallback hooks in case things are wrong. So we
use Netflix Hystrix as a circuit breaker. So Netflix Hystrix has a closure library also, and we wrote our own macro around this library, which is pretty easy to integrate. So as you can see from the code snippet, we are getting a driver rating from an external service and specifying all command key, group key, pool key, etc. Yeah. So Hystrix also provides you a dashboard to monitor your service in a real time. So
we can see how it actually works. So the service is normal. Now it's erroring out, and Hystrix is monitoring it. Right now the errors are increasing, and finally it crosses a threshold. You can see the circuit is open now, and all the calls are short-circuited. Right after a while, the external service recovers, and the circuit closes again and sets to basic normal. Right, you can see it again. So it's erroring out right now, and then it recovers. Right. So Hystrix gives you fallback hooks in case your downstream services are not working properly. Sometimes you can return a default value. Sometimes you can retry the call after a while. It's up to you. And it also provides you the, like all of these numbers are configurable. What is the rate at which you should error out, and what is the time you should retry, after which to check if the downstream has recovered. Right. So this Hystrix was in a very major part in our service. In fact, our dashboard looks much bigger than this. We have around 20 odd graphs over there. So it was very essential for us to keep our service running all the time. Right, this service cannot go down, because if it goes down, everything stops. Right. The another thing we needed to have the service full up, like 100% uptime, is to be able to change all those configuration parameters while the service is up. We can't afford redeploys, restarts, nothing, right? So for that, we use etcd, right? So etcd is a distributed key value store, and it provides you a way to watch configs, right? Watch configs for changes. So the way it works is that we have this bunch of nodes watching the etcd the database all the time. And then a config change request comes in from the load balancer. It goes to one of the nodes. The node notifies or changes the config in the etcd database, and then the database gives you callbacks, all the nodes, right? So the nodes keep an in-memory atom of the config, and when they get callbacks, they update that config, right? So with this, we were able to have no like hot reload of configs without any downtimes. And the Swagger integration that we talked about earlier, it provides you a nice UI in which you can go and change things. So we provided this API in that Swagger UI, and the business people were themselves able to change all these configs as they wanted. The configs, if you are wondering, are things like how much for how far should I look for when searching for a driver, how much time should I wait, etc. These are very business and domain specific configs, so there's no need to have them in a config file and such. We have a backup, another part of config which stays in config files, which is basically thread pool sizes and such, which business people do not care about. So this enabled us to do very quick changes. It actually takes less than a second to increase your search radius from 1 kilometer to 2 kilometer, right? And there is no need to do any deploys or restarts. So we used a bunch of other nifty things. We found them while working on this project. I'm going to share a few of them with you. I'm not sure if you're familiar with this library, Mount. So every long-running service ends up having a lot of state, right? You have connection pools, you have configs, you have external service clients, you have schedulers, and a lot of other things which are stateful and must have a managed lifecycle. You need to start and stop them, and etc. So this one, for example, shows you a scheduler, right? So there's a start function, there's a stop function. This is just a wrapper over the Java's built-in scheduler. So the key thing here is def state. That's where you define a state. You say, this is my state, this is how you start it, this is how you stop it, right? And the schedule function at the end is nothing but just a wrapper over the Java function, right? So why did we use mount instead of, say, component? This is the key part. In component, you would have to use explicit dependency graph. You have to configure and tell which service, which part of which component depends on which component and such. In mount, the dependency graph is implicit. Mount scans your namespaces and checks the imports, right? So if you can see an example here, the archive namespace is the one which runs a scheduled archive, and it does nothing but just imports the previous namespace, the scheduler namespace, and the dependencies are configured automatically, right? So mount will make sure that the scheduler is started before the archival function starts, right? And you have other similar states like the server, the HTTP server itself. So this is how the final main file looks like, a core file. So at the end, you import all the dependencies, all the components that you want to run, and you just say mount/start. And mount will start them in correct order while taking care of the proper dependencies. And to stop, you just add a shutdown hook saying when the service shuts down, you say mount/stop. And it shuts down the dependencies in reverse order also correctly, right? So we have actually some time left. We did not know we'll be able to finish. We were to cover so much. I'll show you another nifty thing we used. So when you're writing very domain-heavy code, a lot of times you need to return an error, right? And either a sort of a success object or an error message. So one way to do that would be to use Java exceptions. You throw an exception in case something like you want to signal an error. Another way to do would be return like particular specific keywords saying, hey, failure, this reason, and such. We decided to go this other way. I'm not sure if you're familiar with this, but either monad is sort of something which comes from Haskell. It has two parts. One is a failure, which is failure message, and a success with a value. So the key part here is this function, right? Bind. It takes a result, which can be either a success or a failure, right? And if it's a failure, it calls the failure function. If it's a success, it calls the success function. So you can use this small snippet of code, and you have this nice-looking, very DSL-like way to bind errors and successes very cleanly. So process booking takes a booking, and it will either return you a success or failure, and then bind will call the post-process booking if it's a success with the result object. Otherwise, where in this case, it defaults to not using a failure function and just chains up the failure. Otherwise, you can also specify a failure function, right? So we use this pretty heavily in our code base, and we found this to be very expressive. You can also chain multiple binds one after another like that. So that is all we had as major points, which we learned while doing this rewrite. If you want to get in details, you can catch up with us. We'll be around, right? So what happened afterwards? So this release went out in November. It's been more than 6 months, and it was almost a game changer for Gojek. We were able to push features much, much faster. We almost did like 1 new release per week because of generative testing and Netflix and all such things we put around monitoring and such. We had much better trust in our code base, right? And yeah, we moved much faster then after that. So we were able to complete the experimentation features that business wanted to be able to do A/B testing and such inside the code base. One issue we found with this rewrite is that getting people up to speed on Clojure, it was difficult in the beginning, right? Because most of our developers come from Java and Go and such, and they find it a little difficult to switch to the functional mindset to write code as like pipelines and such. So we conducted a lot of Clojure sessions. We studied joy of Clojure in those sessions, and slowly people got up to speed. Now we have over I don't know, 15 or so devs working on Clojure projects. We did more rewrites in Clojure. We wrote more services in Clojure. And now Clojure is one of the main languages used in Gojek, right? So yeah, that's all we have. You can find us at these addresses. If you have any questions, you can ask.